Very nice presentation. First, I would like to thank organizers for this very nice conference in a very difficult time for Ukraine. My talk will be about diameter of trees and block graphs. Diameter is some parameter for graphs as diameter or click number, for example. And my talk will be with about joint research result with my colleagues from National University of Kyiv-Mohyla Academy, Dr. Sergei Kozarenko, and our student of master program, Artem Hag. Okay, so in my talk, we consider only simple finite connected simple graphs. I recall that simple graph is this is graph without multiply edges and loops and non-orient. So let we have G. This is a finite connected simple graph, and we define a metric dg on the set of all vertices of this graph in the next way. For any two vertices u and v, the distance dg between two of these vertices equals the length of the shortest path between vertices u and v. Okay, I recall the definition of diameter of graph. Diameter of a connected graph G is a value maximum distances between 2 points, two vertices u and v from the graph V, from the set of vertices of graph. A pair of vertices u and v is called a diameter if a distance between u and v is equals diameter of the graph. For every vertices u, v, and w, we define dg from u, v, w as a sum of distances between u and v, v and w, and v and w. The diameter of the connected graph G is defined as a value maximum of dg from u, v, and w. The triplet of vertices u, v, and w is triameter if diameter. Sorry. Okay. If dg from u, v, and w equals diameter of graph. First diameter of graph was introduced in the article mathematicians Saha and Panigrahi in 2012 in journal Discrete Mathematics. And main motivation was after consider this parameter to characterize ratio of chromatic number of graphs. Later, also this parameter was also used for characterization total domination number of a connected graph, and also the concept of diameter find application in metric polytopos. I recall that tree, and this is connected graph without cycles, and a vertex of degree 1 is the graph is called its leaf. Thus, in his paper, this is a paper on the slide now, diameter of graphs in the journal Discourse Analysis Mathematical Graphs Theory, first decide to study diameter of graph as a parameter, as some characterization of graph. And he showed that always diameter greater or equals than 2 diameters and less or equals than 3 diameters. These bounds are tight. For example, this bound tight, this is true for, we have equality here for path graph. I recall that path graph. This is simplified, yes. So if we have this graph, we have equality here, and if we consider a Petersen graph, then we have equality here. Okay, and also that's proved that there is some lower bound for trees. For any tree, if we have tree with n vertices and l leaves, then diameter of tree greater or equal than this number, this part. Enter the part 4 multiply n minus 1 divided by l minus 1. I call it n. This is number of vertices, and l this is number of leaves. And thus claims that this is a bound, a tight bound, and formulate open question in his paper. First question, is bound, this bound is not tight. What is tight lower bound for diameter of trees? If a tree have n vertices and l leaves, can we find another lower bound? And is it true that any diameter tree of vertices in a tree contains a diameter pair? Is it true that any diameter pair of vertices in a tree can be extended to diameter triples? We give the answer to these questions. And first about trees. So we proved, need to be theorem. We proved theorem that if T as let T be a tree with a number of vertices of tree greater or equal to 4 and number of leaves of tree greater or equal to 3, and then we have this bound for diameter of tree. Moreover, this bound is tight for any given pair n and l. And so we show that this is true for any tree, and for this type of tree, we have equality here. And this tree with 10 vertices and 4 leaves, we start from star with necessary number of leaves with l leaves, and after we continue our passes such that we have necessary number of edges for all this type of trees. Here in this theorem we have equality. Okay, next we consider symmetric even graphs. I recall that connected graph G is called symmetric even if for each vertex U from the set of vertices there exists a unique vertex U prime, such that the set of all vertices is
Освободить тебя. Да, давай я.
Sorry. Okay. Such that the set of all vertices, we can say between between vertices u and u prime. Yes, so this is hold. And for any symmetric even graph, we have the triameter z equals to diameter of this graph. And as follows, corollary, for any n, we have that triameter of a hypercube graph. This is a more famous even symmetric graph equals to n. And every pair of vertices in a symmetric even graph can be extended to a triameter triple. But note that it's not necessary that triameter triple contains that diameter pair contains in triameter triples. So if we have some triameter trip, we cannot say that in this triameter trip there is diameter pair. Okay. So if we come back to the questions of is it true that any triameter trip of vertices in a tree contains a diameter pair? And is it true that any diameter pair of vertices in a tree can be extended to a triameter triple? And we can consider these questions also for different types of graphs. And in general case, it's not true. And for example, for this graph, there is only one diameter pair. This is x and y, and there is only one triameter trip A, B, and C. So this is intersection of diameter trip and diameter pair is empty. Okay, and we now we consider block graphs. A connected component of a graph is its maximal connected subgraph. First, I recall some definitions to define what is block graphs. A vertex whose deletion increases number of connected components in graph is called its cut vertex. And a graph is B-connected if it has no cut vertices. A block graph is a graph is its maximal B-connected subgraph. And a block graph B from G of a given graph G is the intersection graph of the collection of all blocks in G. A graph H is called a block graph if it is isomorphic to B from G for some graph G. There are two characterizations of block graph. We used this characterization in our next theorem. First, a block, this is a very famous theorem of Harari in 1963. A graph is a block graph if and only if each of its block is complete. And the next theorem, characterization of Haborka in 1979, a connected graph G is a block graph if and only if its metric dg satisfies the 4-point conditions for any x, y, z, t. It is called that distance between x and y plus distance between z and 2 are less or equal than maximum of distances between x and z, y plus y and t, and distance between x and t, and distance between y and z. For example of log graph. I don't know, I know green color here will be better. Another. So a graph is block if any block is complete graph. For example, we have here Yeah. Also block, and so on. This is example of block graph. Okay. So next theorem about block graph. Let G be a connected block graph and A, B, C, X, Y such. This is vertices of our graph such that A, B, C, this is a triameter trip of our graph, and X, Y, this is a diameter pair of our graph. Then maximum from distances from A and B, A and C, and B and C equals diameter of G. This means that this triple contains diameter pair, yes, and maximum from distances dg from x, y, a, x, y, b, x, y, c, x, y equals diameter of our graph G. So it means that if we have a diameter pair x, y, we can add any vertex from this diameter trip, and we will have new diameter trip. So this is answer on the questions of DASA to the block graphs. And any tree is a block graph. So if we consider set of all trees, this is subset of all block graphs. And then we have corollary. Let T be a tree, then any diameter trip of vertices in T contains a diameter pair, and any diameter pair of vertices in T can be extended to diameter trip. This is answer on two questions of DAS. And if we consider another family of graphs, this is distance hereditary graphs. A graph G is called distance hereditary if any two vertices U and V belong to a connected induced graph H of G. Then if you have this, yes, then some shortest path connecting U and V and G must be a subgraph of H. That the distance between U and V in H is the same as the distance in A in the graph G. If you consider all trees, this is any tree is a block graph, and any block graph is distance hereditary graph. So we can consider distance hereditary graph as some generalization of block graphs. This statement of last theorem, we cannot extend to distance hereditary graphs. For example, this graph is distance hereditary, and we have tree A, B, C, and diameter pair X, Y. And diameter trip ABC in this graph does not contain any diameter pair because distance between C and B equals 2, between B and A also equals 2, because A and C equals 2, but distance between Y and X equals 3. And the diameter pair X, Y for this distance hereditary graph cannot be extended to diameter trip. So we have diameter trip. This is diameter pair, but if we add any vertex, it will be not triametal chip. Triametal chip, this vertex is A, B, C. Also, I would like, maybe I come back. So this statement of this theorem, we cannot extend to next, the next biggest class of graphs. Okay, and at the end of my talk, I would like to formulate some open questions. Vertex U first is called peripheral if it belongs to some diametral pair, and let P will be a some family of graph. We reformulate some questions of DAS in the next way. Is it true that any triametal trip of vertices of a graph G from the family of P contains a peripheral vertex? Is it true that any peripheral vertex of a graph G from the family P can be extended to triametal trip? Also, I would like to some state about references. This article of DAS. This is all our result was published in the Discrete Applied Mathematics journal in this year. Article published this year, and some characterization of graph. And this article was first introduced the notion of diameter. That's all. Thank you for your attention.